The ideal gas equation is going to combine temperature, pressure, volume, and the number of molecules in terms of moles into one equation and express the relationship between all four of those variables at once. Now, most of the time, we establish the relationship between gases and these various factors in terms of pressure. How are pressure and gas temperature related? How are pressure and volume related? How are pressure and number of molecules related? And we usually do this in the form of proportionality. Pressure and temperature are directly proportional. Pressure and volume are inversely proportional. Pressure and number of molecules are directly proportional. And proportional relationships are good, but they don't allow us to mathematically solve for values either before or after initial conditions, final condition sorts of problems, or to solve for a given amount or one of these four variables if we know the other three. In order to convert that proportionality to an equality with an equal sign into a mathematical equation that we can actually solve, we need to introduce a proportionality constant. And in this case, the constant that is used is represented by the variable r, and this is known as the ideal gas constant. Now, depending on the pressure units that are used, the ideal gas constant may have a variety of different forms. The form that we will use will utilize the pressure units of atmospheres. So for our calculations, we will use as the ideal gas constant 0.0821 liters atmospheres per mole Kelvin. N in the equation that you see, PV equals nRT, stands for the number of moles. R is your ideal gas constant. T would be temperature in Kelvin. And again, P would be pressure and V would be volume. Now, as is the case with most constants, when you rearrange the equation to solve for what that constant would equal, you'll find that the units tend to look fairly strange. But it is because it is allowing us to work with the proportional relationships established by the other variables. So if we take a look at a practice problem, what pressure is exerted by 4.5 moles of gas in a 198 liter container at a temperature of 8 degrees Celsius? Remember that for all gas equations, gas law problems, temperature must be in Kelvin. So if we start with PV equals nRT, we're asked to solve for pressure, so we need to rearrange our equation to be nRT over V. We plug in the moles of our gas. And again, the identity of the gas doesn't matter based on Avogadro's principle and the molar relationship of gases. It doesn't matter what gas we happen to be speaking of here. So we have 4.5 moles of that, ideal gas constant 0.0821 liters atmospheres per mole Kelvin, times our 281 Kelvin, that is the equivalent of 8 degrees Celsius, divided by the volume of 198 liters. We see that the units factor out, moles and Kelvin also factor out, and the liter units factor out, leaving us with units of atmospheres. And this is always a good double check because if you factor the units properly and what you're left with matches the quantity that you're solving for, pressure in this case, then you can be reasonably confident that you have your numbers appropriately placed as well. And when we solve, we should get 3 significant figures in our answer. We should come up with an answer of 0.524 atmospheres. If we look at this example, the question is how many moles of gas, so we're going to be solving for N, can be contained in a 1.44 liter flask at 32 degrees Celsius and 0.923 atmospheres. So rearranging to solve for N, we have pressure times volume over the ideal gas constant times the Kelvin temperature equivalent. And when we plug our values in and factor out the units, atmospheres will factor out, liters will factor out, and the Kelvin units will factor out. You'll see that the units we're left with are moles, but they're in the denominator of a denominator, so the inverse of an inverse is just the unit itself. So the units here would be moles, and when we solve, again, we want 3 significant figures, and in this case we should come up with 0.0531 moles.